So the major benefits of this new technology when it's fully developed would be to eliminate large energy consumption and pollution problems associated with making coke. You cannot charge coal directly into blast furnace because at high temperature, coal becomes pasty, like dough, flour dough, and it'll plug up all the passage of the gases that must happen. So you have to make turn coal into a hard, very hard but porous coal, chunks of coke to support the burden as well as allow gases to flow through. And then again, either eliminate or greatly reduce carbon dioxide emission and also save energy and maintain high reactivity by not having to pelletize these fine ores. Of course, any new technology meets with a number of different technical issues. We've been addressing this in phase 1 work project in terms of the rate of hydrogen reduction. As I mentioned, in order to be competitive, the process has to be intensive. And in order to be intensive, the reaction has to take place very rapidly. In blast furnaces, these burdens go through the blast furnace in terms of hours. That's why blast furnaces have to be huge. Whereas in our process, the reaction time is measured in seconds. So we hope that the reactor can be small, much smaller, and at the same time produce similar amount of iron. As I mentioned again, unlike the flash smelting of copper minerals, which contain sulfur and iron to generate a lot of heat when oxidized, in iron oxide reduction, there's not much heat produced by the reaction, so we have to supply it separately. So how do you supply heat into the reaction? That is a big issue. We have answered that question partially. We still have to develop processes where like burners, which will generate very high temperature yet reducing atmosphere. And there are other technical issues, of course, but we have thought in the past 2.5, 3 years, we have thought about all this, and they have been largely answered towards getting resolution. Okay, in terms of carbon dioxide generation, on the far left, I show you the current blast furnace operation. The next 3 bars represent different modes of the proposed novel iron-making technology. If we use hydrogen, we produce almost no carbon dioxide, just a little bit from limestone that we need to use to produce slag and flux. Now, as I mentioned, the new process could work with methane or natural gas, and the carbon dioxide production will be reduced by about 60%. And even if we use coal, I mentioned that coal contains substantial amount of hydrogen. So even if we use coal directly without making coke, then we take advantage, we utilize the hydrogen content in the coal, and we can still reduce the carbon dioxide emission by about 30%. So there is a substantial, regardless of which fuel / reducing agent we use, there will be dramatic, of course, if we use hydrogen, there will be dramatic decrease, and even if we use coal, there will be substantial reduction in carbon dioxide generation from iron making. In terms of energy, there is also substantial amount of energy savings. Again, the blast furnace on the far left side, and whichever fuel / reducing agent we use in the novel technology, we will get about up to 40% savings in energy. The energy savings largely comes not from the iron making reaction itself, but by not having to go through the coke making and pelletizing and sintering process that is required for the current blast furnace operations. So, so far, the summary of important results are listed here. We calculated the energy savings up to 38% of the blast furnace process, and then complete elimination or drastic reduction of carbon dioxide emission from iron making. And then we've answered the question of whether there is enough rate to produce iron in matter of seconds rather than hours. And as I showed you, the fact that large number of large steel companies are willing to put their resources and fund this research gives me great hope and confidence that the technology is very promising, and the results we obtained so far certainly support that optimism. So where do we go from here? As I mentioned, the phase 2 just signed, the project has been just signed, in which we will do comprehensive bench scale test at the University of Utah facility that I showed you a picture of. It's a small one, but nonetheless, as I said, it's much larger than typical university lab facilities. And then while doing that, we'll design and estimate the cost of doing industrial scale pilot plant operation, and that has to be done at one of the steel company sites. And then that will take about 3 years, and beyond that, we have to actually do the industrial scale pilot tests. And depending on the scale of the operation, it will cost anywhere between $20 and $50 million. Hopefully, we'll go past this stage into a production scale testing facility producing 1 million or 2 million tons per year production scale testing operation. That is my hope, and I'm sure that is the hope of the steel companies putting resources into this development. That's all I have to say at this point. Thank you for your attention.
Thank you, Dr. Sohn. I think what we'd like to do now is open this up for questions to Dr. Sohn, or any other questions about some of the research that's underway through the Institute. Yeah, Scott.
I'm curious about the copper flash furnace example. How big or how much copper can they produce using that technology today?
Well, at the University of Utah, we are very well situated to answer that question, because we have one of the largest copper smelters in the country and in the world, in fact. They produce 300,000 tons of copper per year from a flash smelting furnace that may be about 5 to 7 meters high and a couple of meters in diameter. So it's a relatively small furnace, considering the amount of copper that is produced.